Okay, can you see my slides? All right. So yeah, thank you. Thank you for this opportunity to introduce my research interest and connection with the Athena project today. My name is Younghyun Kim. Since I wasn't able to join in person this wonderful event, so let me take one slide to introduce myself. I'm an assistant professor in ECE department at UW Madison since 2016. And my research interest includes energy efficient computing and communication, security and privacy of embedded systems and mobile systems, and applications of embedded systems. So these three, my main research interests are very closely related to the research thrusts of the Athena project. So in terms of energy efficient computing and communications, this is very closely related to the first thrust 1 and 2, networking and computer systems, which I am also associated with. And security and privacy of embedded systems and mobile systems is closely related to AI foundations, and embedded systems and embedded systems applications is closely related to the fourth thrust, services and applications. So today I'm going to talk about what are my research interests in these three my research interests and how they are connected to the research thrust in Athena, and how I plan to collaborate with the researchers of this team. So I'll be talking about two main topics. One is approximate computing for low power edge AI, and in terms of energy efficient computing and communication. And I'll be talking about precision agriculture as an example of services and applications that we can use low power edge AI systems. So approximate computing is a new paradigm of computing where you trade accuracy for better performance, better energy efficiency, and lower bandwidth requirement and lower storage requirement. So it's an interesting computing paradigm, but it also explores the design space and makes design space exploration extremely more complex due to this additional design space dimensions. Approximate computing is a very promising technology in AI and ML because AI and ML algorithms are intrinsically intrinsic self-healing characteristics. So even if the noise input is noisy and compressed, and even if the internal computation is slightly imprecise, we can still get correct output or still nearly correct output. So it's a very well-known characteristics of machine learning and AI, many AI and ML algorithms. So with that, we typically aim for low power consumption, low latency, or low bandwidth and storage requirements by accepting slightly reduced accuracy. But how does it work in low power edge AI devices, not in high performance cloud computing systems? So in edge AI devices, what I am particularly interested in, I'm particularly looking to as a problem, is that quality is highly input and application dependent. So when we are doing approximate computing, this just average accuracy is not enough. So we typically talk about average, for example, if we are when you are using any approximate computing arithmetic units, for example, we typically talk about energy average accuracy, but that's not enough. I'll talk about that later in the next few slides. And there are multiple approximate computing methods interact across layers and across subsystems. So computing alone is not enough. For example, on embedded systems, especially low power embedded systems, are composed of different subsystems, sensing, compute, and communication, and so on, right? So it's computing alone is not enough. So we need, as a solution, we need a dynamic quality, configurability, and control for adaptive and system-wide energy efficient computing. So in this effort, I've been working on reconfigurable approximate computing methods. And this is an example where we can do arithmetic operations with dynamic reconfigurable accuracy. So the main idea is to do computation in an iterative manner, that instead of taking multiple cycles, waiting until the computation is completed after multiple cycles, this iterative computing method can produce approximate results in all your stage of this computation, but you can terminate this computation anytime during these iterations. So for example, if you're happy with just one very low accuracy result, you can terminate the computation after one cycle. If you need more accurate results, you can, if you can afford more latency, you can wait for 3 cycles or 4 cycles until the accuracy becomes higher. So this enables dynamic accuracy reconfiguration so that we can guarantee higher level quality, not just the accuracy of these low level arithmetic operations. For example, we're not when you're doing approximate multiplication in machine learning algorithms, we're not really interested in the accuracy of multiplications or just matrix multiplications. We're interested in the higher level accuracy, which is typically classification accuracy or prediction accuracy. So this is enabled by a very simple hardware design as shown in the slide. And on the right, you can see the trade-off between the energy efficiency and accuracy of this arithmetic unit compared to other approximate units. So the red curve shows the accuracy and energy and accuracy trade-off of our arithmetic units. As you can see, it's a curve, so meaning that you can dynamically change the accuracy, the trade-off between accuracy and energy consumption with just a single design, whereas in other designs you have to set the accuracy, set just one combination of accuracy and energy efficiency at design time. They're not dynamically reconfigurable. Another challenge in edge AI in low power embedded systems is that energy consumption by non-compute subsystems is substantial in such systems. So approximate computing methods should be aware of the other subsystems and these approximate the methods, low power methods and power management methods should be orchestrated. For example, typical low power embedded systems these smart systems are composed of very high performance sensors and a large amount of memory and storage, and they are often equipped with wireless communication. So you need a holistic optimization of data generation, which is done by sensor, storage in memory and permanent storage devices, processing in CPU or accelerator, or transmission of this data over a wireless channel. So again, that is why the making compute part in low power embedded systems is not enough. You have to think about other subsystems that work with this computing subsystem. So this is an example of our previous efforts in making communication more energy efficient. When you're doing video processing, you're basically collecting data from camera. So when you think about this whole system integration, you have to think about where the data is actually generated from. So this camera to CPU data transmission is quite energy consuming because of the high data rate, high resolution, high frame rate. So we developed a method to reduce the power consumption of this data transfer from the sensor, which is the camera, to the processor by approximating the data and compressing data and reducing the number of data flips on the data bus. So we can successfully reduce the amount the energy consumption for data transmission from camera to microprocessor. So approximate computing for low power ML, I think designing cross-layer approximate computing for efficient ML computation is important. And we are looking at cascaded and nested quality control loops in circuit, architecture, and software layers, meaning we have to control this quality and accuracy at different layers of abstraction, computation abstraction, not just a single control loop that controls this circuit level, architecture level methods from the upper high level application. And also we are working on design frameworks, developing design framework for joint optimization of subsystem that enables system-wide energy accuracy trade-offs. So the synergy I'm looking for with the Athena team is that in the networking thrust, I'm interested in working with other team members on joint approximate computing and communication. I'm also interested in low power edge AI applications that I will be talking about in a few minutes. And I'm also interested in making ML training and inference faster and more energy efficient. And I'm interested in scalability and security of edge AI devices in collaboration with the AI Foundations team. All right, so I'll spend a little 1 or 2 minutes on the applications of edge AI device systems in precision livestock farming. Applications of AI in precision livestock farming is very important because we can improve productivity. The margin in US dairy farm is becoming thinner and thinner. It helps, so we need to help farmers making decisions on farm operations, and we want to reduce the requirements for skilled labor. And we can promote animal welfare, of course, by preventing and controlling animal diseases. And we can save water and energy by precision controlling. So this is an example of AI, applications of AI in dairy farming. This is a photo we took in a partner farm in Wisconsin. AI can be useful for herd behavior analysis, disease detections, and also energy saving fan and sprinkler control. But applying AI is not trivial, especially when you consider these poor internet connectivity. So on the left, you can see the locations of dairy farms in Wisconsin, and in the Clark County in Wisconsin, where you have a lot of dairy farms, high-speed internet is not available across the county. So it's sending all the data to the cloud for powerful processing is not an option here. So we want to apply AI, edge AI technology in precision livestock farming. In terms of vision, we can do posturing and behavior analysis, identification and localization of the cows. Networking, we want to enable ultra low power wireless network for low cost wearable sensing and prediction and decision making for microclimate control and disease and fertility management. So synergy with the Athena team in this application domain, I want to work with the team members to enable edge ML under network connectivity constraint and enable application-aware network configuration for low power sensing and monitoring, low power, low cost AI accelerators for practical distribution of edge ML applications in the farm. So thank you. I'll be happy to take questions